Hi everyone. Okay, so jump ahead again to the next section on radicals, multiplying and dividing radicals. Remember, we're going to do this with variables soon, so we really want it to make sense with numbers. Okay, so we have our property. We've used it before. We know that if we take the square root of something, or any root, so let's say the nth root of x times the nth root of y, they do have to be the same root. That matters. I don't know if I gave you an example of that not working, but it does matter. You can combine that into a single radical. Multiplication, division play nicely with roots and exponents. Addition and subtraction absolutely do not. So here, and there's kind of a two options thing going on here again, maybe even three, but I'm just going to show you two. We can jump straight to that property and say, okay, the roots are the same, so I can combine that into a single root of 2 times 8, which is 16, and that's very nice. Square root of 16 is 4. You could, so I'll just say what the two other things are since this worked out so nicely. You could extract roots from the 8 first. I don't think that would make this one necessarily easier, but it's an option. The other thing that I watch for, and this will be better in an example that doesn't work out quite so perfectly, is things like this, where when you mush it together, you're going to build a perfect square. So there's a factor of 2 in the first one and a factor of 2 in the second one. And once those go together, you have a perfect square. And in this case, you happen to have only perfect squares, which is kind of nice. So I'll bring it up again when we have one that's going to have some different simplification. But that's what we're going for. Multiply the radicands, the thing under the root. Simplify if possible. Done. Okay, so in this one, I have prime numbers, which is kind of nice with radicals. You don't have to worry about extracting any roots. So here, when I mush them together, I have root 5 times 11, which is root 55. Always want to think twice about the possibility of extracting roots, but I definitely didn't build any perfect squares. I can't factor out anything nicely from 5 or 11, and when I put them together, I still can't. Okay. 6 times root 3 times root 21. So this starts to get a little more interesting because notice, root 21, not a perfect square, none of its factors are perfect squares. Its factors are 3 and 7. But when we multiply by that root 3, all of a sudden, we have root 3 times 3. Here, I'm trying to think how to write this out so I don't mix you up. Root 3 gets mushed in, times another 3 times 7. So if you're watching, rather than have to figure out what 3 times 21 is, not that that's that bad, but sometimes they're messy, you could say, ooh, I can see that I'm going to get a 3 squared out of that. So I'm going to say I have 6, square root of 9, square root of 7. Feel free to skip a step as you get comfortable, which is 6 times 3 times root 7, which is 18 root 7. Okay, so I don't know if that was very convincing. That might have just looked like math. So absolutely feel free, especially when the numbers aren't too terrible, to say, okay, well, I'm just going to multiply. 21 times 3 is 63. And then I'm going to look for factors that are perfect squares. And I can still get there. So totally up to you. But if the number under the root starts to get really big, you might want to try splitting things up earlier to see what's going on. I'm going to go ahead and jump to 18 root 7. So you can look for those perfect squares a little sooner if you would like to. Okay, next one looks scarier than it is. People want to distribute and FOIL and do all sorts of crazy things, but there's no addition or subtraction in this. There is a negative number, -6, but it's not subtracted from anything. So we're just multiplying, and the beauty of multiplying is as long as you don't have any other operations in the mix, you can just rearrange order at will. We do have some square roots in the mix, right? So those matter. But we can still rearrange the 2, the root 20, the -6, and the root 35 as much as we want. So I'm going to rearrange like this. 2 times -6 times root 20 times root 35, which is going to give me a -12. And then, again, this is up to you what you like better. If I multiply 20 by 35, I'm getting 700. So here, we can do that. Or you could say, kind of looking in advance, this is 4 times 5, and this is 7 times 5. You could separate off those two 5s. So we'll go through 700 again, doesn't sound so bad. Every once in a while you get something that's a little hard to spot. I like 700 because I know that 100 is a factor of 700, and I know that 100 is a perfect square. We're not a room. So I get negative 12 times 10 times root 7, which is negative 120 root 7. Okay, showing lots and lots of steps. You don't have to. People always get worried that I'm going to expect to see that many. Whatever works for you is great, within reason. If you show me 0 steps, I can't see what you're thinking at all. And sometimes that's not okay. Sometimes it is, sometimes it's not. If in doubt, ask. Okay, cube root of 20 times cube root of 36. So here, I would think the difference would just be in the simplify. Okay, so let's see. 2 times 36, 772, so we get 720. Maybe this is a little bit better example. I'm trying to find perfect cubes that are factors of 720. And I feel like 9 probably goes in there, so I could do it. But maybe here's when I should finally show you the other way to kind of split that up. So we could, instead of mushing everything and doing the multiplication, we could say, okay, well, let's actually split it up a little more. Ooh, and I'm even seeing, oh no, cube roots. 4 doesn't really get very exciting when you're taking cube roots. Same thing with 36. If you were tempted by that, it is a perfect square, it's not a perfect cube. So I am seeing over here 36. What do I want? Maybe 9 times 4? No, maybe we'll go even further. We'll say we have 2 times 5. And over here we have 3 times 3 times 2 times 2. So those prime factorization things, right? And we're looking for groups of 3. So what I see is that I do have 3 2's. So I would like to separate an 8 out. And I think I might just go back to my 720. Promise not to torture you with huge numbers all the time, but we do need to know how to break these down. Okay, so 720 divided by 8. I think that's going to give me 90. 8 times 90. 9 times 8 is 72. Yeah, okay. So maybe I could have figured that out without the factors. I don't know. And then we can take the cube root of 8. That gives us a 2. Cube root of 90, I think we're pretty stuck with. 9 is a factor of 90, but we would need 27 for it to help us. 8 is not a factor of 90. 9, 27, 64 is too big. So I think that we're good there. I don't think we have any more perfect cubes in the mix. What do I have going on here? Oh, still multiplying. Right. Okay. So last one here, and then I'll cut the rest into another video. This one's already long enough. This again is just realizing that you can rearrange, and also realizing that 4th root of 48 over 3 is the same as 1/3 times the 4th root of 48. So I'm just going to rearrange and say I have 8 times 1/3. Ooh, maybe I'll switch colors here so that you can tell what's going on. 8 times 1/3, I've got pen lag here, times root 54, 4th root of 54, times the 4th root of 48. Okay, so 8/3 out in front, that's fine. 48 times 54, okay, this is getting to be a good example as well, because I don't really want to figure that out in my head. So if you have a calculator and want to do some number crunching, you can, but you can also say, okay, how do I get 54? 54 is 27 times 2, so that's 3 cubed times 2. 48, what is 48? 16 times 3, so 4 squared times 3, and I'm looking for a perfect 4th power, and I can get it with the 3's. So I can say, okay, I'm going to split this up, and I'm going to split off 3 to the 4th. 3 cubed times 3 is 3 to the 4th. And then I'm going to go ahead and leave. Ooh, actually, no, I'm not going to leave it because I went to 4's, but I can go down to 2's. 4 squared is 2 to the 4th, right? 16 is 4 squared, but it's also 2 to the 4th. So I can take out 4 2's as well. Actually, just for free, I didn't even need to multiply to do that. And I'm going to be left with a single 2. Okay, so I have 8/3 times the 4th root. Oh, I'm going to go ahead and start doing some of these. Okay, so I can take the 4th root of 3 to the 4th. That's going to give me 3. I can take the 4th root of 2 to the 4th. That's going to give me 2. I can't take the 4th root of 2, so I'm just going to go ahead and leave it. And then just a tiny bit of cleanup. I can cancel a 3, and 1 is left over. 8 times 1 times 2 is 16 times the 4th root of 2. That as well as I can simplify. Okay, I will split off division for a separate video. Thanks for watching.